All right, so we have kinetic energy. Another type of energy that we have is called potential energy. And within potential energy, you can have several different types of potential energy. Like you can have thermal potential energy. We'll look at gravitational potential energy first, but then later we'll look at thermal energy. Uh, we're going to call this U, and U is this potential energy. It is stored energy or work. A good way of thinking about potential energy, that it has potential for motion. Potential for motion. So, if I have something and I hold it right here, it has the potential for motion. If I let it go, it'll move. So I talk about how it has potential energy. We can also see that like with rubber bands. I don't have one up here, but if I have a rubber band and I stretch it, it has the potential for motion, because if I let it go, it'll shoot across the room. Also in food energy, that's more of a chemical type energy, but it is also potential energy. It can be converted into motion. And we'll talk about that later when we get into the body part. There are many different types of potential energy. The book goes into this a bit. They include elastic, like a rubber band, gravitational, and electric potential energy. We'll get into this in one of our last chapters. But if I have charges that are near one another, they have the potential for motion. Because like, for example, if I bring two charges together, they'll either attract or repel one another. If I have two like charges, say two positive charges, what do those do, attract or repel? Two similar charges, they repel from one another. And so they have potential for motion, because if I let them go, they fly apart from one another. So anytime you have the potential for motion, that is called potential energy, just sort of as a generic term. Let's say that I move an object to an height h. So I have some object of mass m. It's on the ground. It's at a height h equals 0. And then I move it. I apply a force to it in this direction and move it up to a height h. Right, think about the force that's required to move this object in order to move it from this position to this position. And then I want to ask you, what is the work that has been done on this object? What is the work on the block? And remember, work is just force times displacement. So you need to think about what is the work required to move this block, and then what distance does it travel. Which of these describes the work done to move this block? Is it the mass times gravity divided by the distance, h? Is it the force over h? Is it mg times h? Or is it m over g h? Which of these represents the work done on the block when I move it from a position of h equals 0 to a height h? Is it mg over h, f over h, mgh, or m over gh? Which of those represents the work being done on the block? What is the work done on the block? Think about what work is. Work is the force times the displacement. And so now think about the force required to move this block, and what is the distance that it goes. Alrighty, let's stop at say 110. 110. Okay, let's see. A or C? Um, it's C. Because remember, our force, the force that we're concerned about is the force weight. In order to move this block, we need to have a force that is at least equal to the weight, a little bit more than the weight, to move it up from this position. So our force is equal to the mass times the acceleration due to gravity, which is equal to the weight. Our force is equal to the weight, which is equal to mass times gravity. And so the work that's being done, which is force times displacement, is going to equal to m times g times h. Okay, but remember that we have this idea, the work-energy theorem, which says that when I do work on an object, I change its energy. So if I have this object up here, it has a speed equal to 0. I've just moved it up to this position. I've converted the work that I've done on it, that m times g times h, to what type of energy up here? Is it kinetic or potential energy at this point? What type of energy does the block have? Does it have potential or kinetic energy? It has potential. It doesn't have any kinetic energy because the speed is 0. So up at the top, all of that work, remember, which is mgh, has been converted into potential energy. And so the expression that we use for gravitational potential energy comes about from this quantity for the work. It's equal to m times g times h. So an object, if I bring it a certain height from the floor or from the surface of the Earth, it has a potential energy that's equal to its weight, which is mg, the mass times 10, which is the acceleration due to gravity on Earth, times this height h. And then when you drop the object, so if I have the object here and I let it go, all of that potential energy is now converted into kinetic energy. That makes for a pretty useful way to calculate speeds and what have you, and we'll get into that next time. Right now I want to show you a video. It's from the PBS series, The Circus. You ever watched that series? No, it's like a reality show where they follow a circus around, but they also created these extra videos about different topics in physics. And so this is about, see, I think this is about the lady on the balance beam, where they use this, well, I'll just show you this. Oh, shoot, I'm not sure if I have it here. I'll Google it. I think I might have some clicker questions as well. Let's do a few of these last 5 minutes. All right. Is it possible to do work on an object that remains at rest? Yes or no? A, yes, or B, no? All right. I'll stop at 30. Okay, B is right, because if an object is at rest, there's no displacement. And if there's no displacement, there's no work done. A box is being pulled across a rough floor at a constant speed. What can you say about the work that's being done by friction? Does friction do no work at all? Does it do negative work, or does it do positive work? I'll stop at 30 seconds. awesome. It does negative work. Remember, because the frictional force will always oppose the direction of motion. Almost always. There are a few special cases where it doesn't, but almost always oppose the direction of motion. And that means it's going to do negative work. Everything okay, Jocelyn? In a baseball game, a catcher stops a 90-mile-an-hour pitch. What can you say about the work done by the catcher on the ball? So this catcher catches this 90-mile-an-hour pitch and makes it come to a stop. What can you say about the work that's being done by that catcher? Is it doing positive work on the ball, negative work on the ball, or does it do zero work on the ball? Think about the concept of what positive and negative work means, or zero work. What does that mean physically to the object? And then it should give you the answer. Remember, the positive and negative doesn't refer to a direction. It refers to something else that the work does. What does the positive and negative mean for work? If I have positive work, what does that mean it's doing? Increasing the energy. If I'm doing negative work, decreasing the energy. So think about what this work is doing. Is it increasing or decreasing the energy of the ball? I'll stop at 108. Okay, the right answer is B. Okay, it does negative work. It's like he's taking energy away from the ball. He's doing negative work. A ball is tied to a string, is being whirled around in a circle. What can you say about the work being done by tension? You might not know this right off, but think about it for a second. I'll lead you into the answer in just a bit. Think about the tension. What kind of work does it do? Think about the displacement of the ball, and then think about the direction of the tension. And then that should tell you the idea. If they're in the same direction as positive, opposite directions as negative, perpendicular as zero. What is true about the tension in the string and the displacement of the ball for this scenario? Okay, we're about half and half, slightly less than half and half. What is the direction of the displacement? At each point, the displacement actually changes, right? But at each instant, my displacement is going to be in this direction. Up at this point, for example, it'll be in that direction. But at each point, the displacement will be tangent to the circle. And the tension is always going to be towards the center of the circle, because you have this ball and you're spinning around on a string. That tension is always going to be towards the center of the circle, and so that means the answer will be no work at all, because they're perpendicular to one another. That means no work at all. All right, we will have a quiz at the beginning of class next time. We will not have class on Thursday. You have a great day. Thanks for your help today, okay? I really appreciate it.